Hello, everyone, and welcome to the chain rule. So I'm just going to warn you, some people find this a little bit tricky, but if you do not understand it completely today, I assure you in the next unit, when we do something called related rates, it'll all become clear. So do not panic. I don't even give a quiz on this yet because I realize that it's a little bit tricky. So find the derivative of y is equal to 3x plus 4, the quantity squared. You do this problem using what I have referred to as taking the derivative of the inside. You would say y prime is, you bring down the 2, the entire 3x plus 4 goes to the first power, and then you multiply by 3. You have no idea why you do that, but you trust me, which I love, and it gets you the right answer. Today, I'm going to tell you the theory, the logic behind that. Believe it or not, there are actually two different ways of thinking about it. So hopefully one of the two will make sense to you. So just a little background. Calculus was invented by Newton. He was actually using it just as a tool. He didn't publish any articles on it. He used calculus in order to do physics. And then this guy, Leibniz, came along and he also simultaneously came up with calculus and he did publish his work. And then Newton came back and said, no, I've been doing this for years. So little history there. But what happened is that they have two different notations. And it's actually a good thing because the two different notations will serve you well in different ways. Very similar to how sometimes y is nice and sometimes f of x is nice. In derivatives, sometimes we're going to use the f prime notation and sometimes we're going to use the dy dx notation. So here are the two rules. I'm going to actually do an example to explain them. I think it'll be easier. So Newton's way, taking the derivative of the inside. So you guys probably prefer, because I've taught you to prefer, this method of writing a composition of functions. I really like it. When somebody says to me f of 1, I know that that means plug 1 in. When I see f of w, I know that means to plug w in. And when I see f of g of x, I know that that means g of x is getting put into the f function. You're composing two functions. However, as much as I love this notation, I will say that this notation is going to be easier for calculus. F of g of x. It's an unusual notation, but it does actually correspond with other things that we do. If I said f plus g of x, well, that means f of x plus g of x, but it's an easier way to write it. Or if I said f over g of x, you would instinctively know that that meant divide f of x and g of x. Well, same thing here. This means f of g of x, which is actually how you would pronounce this first one. Why is it easier? Because when I want to take the derivative, I know exactly where I want to put my little derivative mark. I want to put it right here. F of g, the derivative of x, where when it's in this notation, people get confused where they should put it. So f, the derivative of f of g of x is going to be, now think about what you guys do. You take the derivative of f, but you leave g the same. You don't touch it. So I'll give you an example. Here's 2x plus 3, or 2x plus 1 to the third. 2x plus 1 to the third. So this is your y. Your y prime is going to be, you're taking the derivative of f, 3 times something squared. But you're leaving g, the inside, the same. And then, I'm using this theory up here, you multiply by the derivative of g. So then I multiply, remember this is g in here, I multiply by 2. And I get 6 times 2x plus 1 squared. So this derivative of the inside that you've been using is literally this. derivative of the inside. You've been doing it for a long time now, and you're very good at it, but now you can see the notation behind it. Unfortunately, as good as this notation is, it doesn't help you with a whole variety of problems that we're going to be doing this year. And Leibniz's notation is going to be fantastic. So I'm going to teach it to you today using some simple examples, but you'll probably master it in the next unit. So I'm going to think of this problem, y is equal to 2x plus 1 cubed. I want to know dy dx, but I can't do it because it's not just a plain variable. So I'm going to switch it to y is equal to u cubed, because that has a very straightforward derivative. Dy du, let me just put a question mark over there, that's what we're trying to find, is 3u squared, basic property of derivative. What is u? U is the 2x plus 1. What is the derivative of u with respect to x? So if you take the derivative of u, and x is the thing you're doing stuff to, you get 2. And here's the key. Dy dx is dy du times du dx. Because even though I don't really want to do it, this would cancel. See, dy dx is equal to dy dx. The du's would cancel. And that's why this works. So how can I actually put it together? Dy dx is equal to 3u squared times 2. I do have to put the u back in. You're thinking, who would do it this way? Nobody would do it this way. But hopefully it helps you understand why you take the derivative of the inside. This is the y behind the derivative of the inside. Number 1 is really just a notation issue. I want you to understand the notation of it. All right, I will do one more to help you understand this, and then we'll just do some basic problems. So in this case, remember, these two I'm going to do often because people get them confused. This is actually sine of x, the quantity squared. So I want to know dy dx. I'm going to say that u is sine of x, and then I can find the derivative of y with respect to u. Because now, if u is equal to sine of x, then y is equal to u squared, which is a very straightforward derivative that I can do, 2u. And what is the derivative of u with respect to x? Here's u. The derivative of u with respect to x is cosine of x. So what is dy dx? Dy dx is dy du times du dx. Because if I canceled the du's, I would have dy dx on the left and dy dx on the right. So dy dx is equal to dy du, 2u, times cosine of x. You can't leave it that way. U is sine of x, cosine of x. And, of course, I'm going to keep reminding you, especially if you're in AP, that sometimes a multiple choice answer will be written as sine of 2x, just to see if you remember that trig rule. Okay, last one. U is going to be equal to x squared. Why did I do that? Because a derivative that I do know is sine of u. That's a basic derivative. No insides are needed. So now I'm going to do dy dx. That's what I'm trying to find. but I can find the derivative of y with respect to u. So here's my y. Use the thing I'm doing stuff to. I get cosine of x. And what is the derivative of u with respect to x? 2x. See how there's no derivatives of insides? We've eliminated them by following this concept. So dy dx is dy du times du dx. Dy dx is equal to dy du cosine of x. Oops. Look at that. I made a little tiny mistake there. Cosine of u. We were taking the derivative with respect to u. Cosine of u, du dx to x. And then I have to put this back. Cosine of x squared. So remember, u was x squared. So that's what I have to put back. Times 2x. Or if you want to put the 2x out in front so you don't accidentally write 2x cubed, that would be a very safe thing to do. That's the derivative. Okay, so I can't stress enough. If you're like, I kind of get it, but not completely, don't worry about it. Okay, we'll have this come up again later in the year, and I assure you, you will get it then. All right, this I do want you to focus on for today. You'll see some homework questions like this. These are not bad. This is pretty much doing hypothetical derivatives. So it's pretty much, can you follow all the rules of derivative? Evaluate the derivative with respect to x. So if this is your function, then the derivative is 2f prime of x. What is this trying to teach you? That a 2 on the outside stays there. It's a constant. It just gets multiplied by the derivative. What is 2 times f prime of 2? Because I want to know it at x is equal to 2. I look up at my chart. F prime of x at 2 is 1/3. 2 times 1/3 is 2/3. If we were in class, that is literally the only one I would do for you, and then I would walk around. So if you would like to stop, pause the video. I will quickly list the answers off to the side, and you can write them down, and then you can check as you go. 15 minus 8 pi for C, 37 over 6 for D. E is -1. F is 1 over 12 square roots of 2, or you can rationalize the denominator. But they don't tend to do that in AP, so we're going to let it go. And G, right? So you can write down those answers in your margin. If you get them right, you can skip this whole portion of the video. All right, for people that need to see it. So when you're taking the derivative of two separate terms, this is just trying to remind you that you can do them separately. Now they want to know f prime at 3 plus g prime at 3. I look at my chart. This time I look at the 3 and the f prime, and I get 2 pi. I find the 3 and the g prime, and I write 5. Next one's a little trickier. F of x times g of x. It is not f prime of x times g prime of x. Wow, those primes did not want to come out today. Okay, bad. No, don't do it. Instead, you need product rule. So this is going to be the second times the derivative of the first plus the first times the derivative of the second. They want to know this derivative at 3. So I'm going to plug a 3 in there. Some of you are skipping that first step and plugging the 3 in right away. and that's fine too. I have to look at my chart now. I'm only going to use the row with the 3, but g of 3 is -4. F prime of 3 is 2 pi. F of 3 is 3. And g prime of 3 is 5. And that gives me the -8 pi plus 15. That is the answer. So hopefully after my big evil face on the last one, you know exactly what you're supposed to do for this one. Quotient rule. The bottom. Let's skip right to the 2 this time. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Notice I switched to brackets. I think it makes it a little easier to make sure you have all of them accounted for. So g of 2 has its own parentheses, and then there's brackets for the square. Again, I need to fill these in. So g of 2 is 2. F prime of 2 is 1/3. F of 2 is 8. G prime of 2 is -3. G of 2 is 2. And by the way, these don't cancel. You have a g of 2 on top and a g of 2 on bottom, but this is stuck in this term. You can only cancel factors, not terms. So this gives me 2/3. Okay, actually, let me just stop here and say, if you're in AP, not on my test, but on the AP exam, stop here. They do not require you to do the simple math. I do not want you to do that, because if you make a mistake going from here to the answer, you could lose a point. But since they allow you to do this, you might as well do it. But if this is a multiple choice question, then you are going to need to know how to do this. So the easiest thing to do, because in a multiple choice they're not going to leave it like that, is to multiply the top and the bottom by 3. When I do that, I have to get out my calculator. 24 times 3, so I don't want to make a mistake, is going to be 72. 3 times the 2/3 is going to be 2. And on the bottom, I get 12. That's 74 over 12, which reduces to 37 over 6. So if this had been a multiple choice question on the AP exam, you're going to see it as 37/6, which is how they see if you know how to do the math. But on the open-ended, you should stop at that green spot. Okay, starting to get hard. F of g of x. So this is just like the one with the 2x plus 1 cubed, right? You're going to take the derivative of f, but you're going to leave g the same. Isn't that what you would do? You would take the derivative of the f, but look, you would leave g the same. But then you would multiply by the derivative of g. I cannot stress enough, this is definitely one that you need to know and understand. Very, very tricky. It's how we started the class. Can I call it class? How we started the video. All right, it's actually still a hard problem. I'm going to put in my 2. So g of 2, and then g prime at 2. Oop, that last parentheses not needed. Okay, g of 2 is 2. G prime of 2 is -3. But I had to work my way out. So g of 2 is 2, and now f prime of 2 is 1/3. So 1/3 times -3 is -1. Pretty challenging problem. For the next one, what do you always do when you have one of these? The square root should always be switched to a 1/2. And again, how do you take the derivative of something, anything, to the 1/2? If you had something to the 1/2, you would do 1/2 f of x to the -1/2, right? You would leave that the same, bring down the 1/2, make it to the -1, but then you would do the derivative of the inside. Now I'm going to do this for 2. So 1/2, if you want to, you can move this to the bottom, square root of f of 2. Right? -1/2 is a square root on the bottom, and then the f prime is on top. But I'll just leave it off to the side for now. Make sure I don't lose anybody. Times f prime of 2. So this can move to the top, or maybe I'll just put over 1. When you're doing a fraction times a fraction, think of it as over 1. So f prime of 2 is 1/3. And f of 2 is 8. Again, if you were doing the AP exam open-ended, I would stop here. If not, I would first clear the fractions. And now I have 1 over 6 square roots of 8. And I would change the square root of 8 into the parts I can do and the parts I can't. If you're wishing for some good old days, do you remember when the only thing you had to do was take the square root of 8, literally algebra 2? Parts you can do and parts you can't. And that was a test question. Those were the days, right? Now that is literally one tiny step in a big problem. Honestly, you should be so proud of yourself. You've come really far. Last one. If this were really my problem, if I really had 1 over 2x plus 1 to the squared, I personally would change that to 2x plus 1 to the -2 and then find the derivative. So always make it a real example. So I'm going to change this to g of x to the -2. And then the derivative is -2 g of x, it doesn't change, to the -3 times the derivative of the inside. At x is equal to 3, I have -2 g of 3 to the -3 times g prime at 3. The -2 stays on top. This moves to the bottom. So g of 3 is -4, but that's going to get cubed. And g prime of 3 is 5. That gives me -10 over negative, cubed is -4 times -4 times -4, which reduces to +5 over 32. Great. Good job, everybody. Pretty hard little set there. I am not going to do the challenge for you. If you would like to try it, it is pretty intense. It's really in there when, you guys can picture yourselves sitting around in class working. You always got that kid, right? That's like finished the whole section already. And this keeps them busy. I'm not going to give you one this hard. But if you can get that, you should be unbelievably proud of yourself. Okay. For each of the following, use composition to find f of g. So again, this notation's better in this case because that way you know where to put the prime. So this is really just practicing composition of functions. This should be an easy section for calculus, a hard section for algebra. So they want f of g of x and then the derivative. So f of g of x. That means I'm going to take this equation, and what am I going to put in for my u? What am I going to put right there? G of x. I'll change the color so you can really see what I'm doing. Honestly, the hardest part about this problem is the algebra. So I have a top and a bottom. I'm going to multiply the top by 1 minus x, and I'm going to multiply the bottom by 1 minus x. Why? Because then those canceled. And back to my blue, I get 1 minus, what's left? 1 minus x. On the bottom, just 1, so I'm not even going to write it. This simplifies to 1 minus 1 plus x, which is x. This is fantastic. What is f of g of x? What's its derivative? 1. Easiest calculus you're going to do all day, but really hard algebra. As a second option, in case you're not good at that multiplying by the top and the bottom, if you have this, you can make this one also into a fraction, 1 over 1, and then you can flip this one and multiply if that's easier. Keep the first one, but I change it to a fraction. Change it from division to multiplication, and flip, I believe, is how you guys are taught. I still like flip and multiply. And then so 1 over 1 minus x becomes 1 minus x over 1. You'd get the same thing if you don't understand the way I did it in red. Number 2, so I want f of g of x. That means I'm going to put g of x in f of x. There's 2 places that I'm going to put it, and I get pi x plus 1 over cosine squared pi x. This one doesn't have any fancy algebra, but it does have some more challenging calculus. I personally am going to change this to cosine of pi x to the -2. I think that that's easier. Whenever I have a constant on top and a power on the bottom, I personally find this the easiest way to do it. So the derivative of f of g of x, the derivative of the first term is just pi, and the derivative of the second is -2. Keep this the same. A lot of people take the derivative right here. Not yet. To the -3. Now, okay, this is the inside, and it's going to have its own inside. So when that happens, sometimes I just work off to the side. W is cosine of pi x. If you were doing this derivative, dw, maybe read those Arthur books, dw dx is negative sine of the same thing times the derivative of the angle. So all of that is what goes here. And this is definitely a step that people miss. They miss it because they've already done so much derivative. When they see the derivative for cosine of pi x, they just write negative sine of pi x. But if I had just given you cosine of pi x on a quiz, you probably would have gotten it right and remembered the derivative of the inside. But when it's stuck in a bigger problem, people tend to forget it. All right, final answer, pi. Now the negative and the negative will make a positive, plus 2 pi sine pi x over cosine of pi x cubed. Or you can put the 3 next to the cosine. So interesting little problem here is, oh, I was going to say they want it at 1/4. I was going to say, I don't know that answer. If they didn't ask it for you at x is equal to 1/4, I will say, just for AP, that if this is a multiple choice, they would love to do something like this. 1 plus 2 pi tangent of pi x secant squared of pi x. Where did they get that? One of the sines over cosines makes the tangent, and then the other two cosines that are left can be written as secant squared. So, little note, multiple choice is going to be tricky on the AP exam because they're going to give you annoying answers that you're going to have to puzzle out. Okay, but they want f of g of x at x is equal to 1/4. So now I have 2 pi sine of pi fourths over cosine of pi fourths cubed, which would be pi plus 2 pi square root of 2 over 2. I'm going to act like somebody raised their hand for that and made my day awesome. One of these cancels. So this one and one of those cancels. So now I have pi plus 2 pi over, so the square root of 2 over 2, when you square it, is going to be 2 over 4, because the square root of 2 squared is just 2, and 2 squared is 4. I'm going to flip and multiply. So instead of doing 2 over 4, I'm going to multiply it as 4 over 2. Now my 2's cancel, and I have pi plus 4 pi, which is 5 pi. Okay? On the outside chance, not the outside chance, but on the chance that you're getting this, I will tell you that the answer to the next one is -8, if you would like to stop and do it on your own. This is the last one of this type. Composition, f of g of x. Don't worry about derivative yet. Let's just do the composition. So this is f of u, but I want f of g of x. So I'm going to put a g of x in everywhere that I see a u. It's going to be ugly. 1 over x squared minus 1, that's u, minus 1, this is this minus 1, all over, again, 1 over x squared minus 1, and then this plus 1. And all of that is squared. Not easy. 1 over x squared minus 2 over 1 over x squared. And the whole thing is squared. Okay, I'm going to do something tricky. Within the square, I'm going to still ignore the square because I don't want to have to do FOIL. I'm going to multiply this by x squared and this by x squared. I'm going to clear the fraction by multiplying the top and the bottom by the same thing. When I do that, I distribute this to both of these, and I get 1 minus 2x squared over 1. Well, that was worth it. So now you have a decision to make. Do you want to FOIL that out and then do the derivative, or do you want to do chain rule? I personally would do chain rule, so that's what I'm going to do. That gives me 2 times 1 minus 2x squared to the first times the derivative of the inside. That was easier, in my opinion, than FOILing. They want to know f of g prime at -1. So I have 2 times 1 minus, now since -1 is being squared, it's +1. +1 times -2 is still -2. And -4 times -1 is +4. So now I have 2 times -1 times 4, which is -8, which is the answer. I hope you tried that one on your own. It's still really tough, though. Thanks for hanging in there, guys. Okay, this is a teeny tiny little taste of something that we're going to do in the future, just to kind of get your brain thinking about it. Suppose the velocity of a falling body, not like particle body, not real body, is v is equal to k square roots of s meters per second. At the instant the body has fallen s meters from the starting point, show that the body's acceleration is constant. So I'm always going to write this off to the side, SVA. So if the velocity is k is just a constant, square roots of s, or better yet, ks to the 1/2, then the acceleration is the derivative of that, k over 2 s to the negative 1/2, okay? But here's the problem. We have been a little lazy about just saying the derivative. It's actually not true. The derivative of velocity with respect to time is acceleration. Well, there's no t in this equation, so you can't do the derivative of the velocity with respect to time. This is where chain rule comes in. You say, I want dv dt. How can I get that? Well, I have an s in my equation. I'll do the derivative of the velocity with respect to s, and then what do I have to cancel that with? It would cancel if I put a ds up here, and I need a dt in my answer. This is just like what we did a little while ago. This is the chain rule. You are not going to be expected to do this yet, but I'm trying to put it in your head because I'm a big believer that if you have it just even a morsel of it in your head now, then when I go to do it in a month, your brain will have already started processing this concept and it'll go easier for you in a month. So the derivative of velocity with respect to time is acceleration. The derivative of velocity with respect to s is what we started to write before, 1/2 k s to the negative 1/2. Now you might be thinking, how am I supposed to get the derivative of s with respect to t? I'm just going to tell you right now, this is really, really tricky. Give you a second to think about it. The derivative of s with respect to time is velocity. Remember, in our SVA series, if you take the derivative of the s equation with respect to time, you'll get velocity. If you take the derivative of velocity with respect to time, you'll get acceleration. So I can replace that. I'm going to move my s to the bottom. I can replace ds dt with velocity, which is k square roots of s. My square roots of s cancel, and you get 1/2 k squared. K is a constant, and it's being multiplied by a constant, so is a constant. Show that the body's acceleration is constant. I did it. If you're even a little bit thinking, I never could have done that, you will, I promise. But now to blow your mind, now I'm going to make you feel good about yourself. We're going to do a nice, easy one. If you were going to take this derivative, you would probably just write y prime. But in this case, they want to know the derivative of y with respect to t. So y prime is a bad notation because it doesn't tell you what you're taking with the derivative with respect to. The only derivative you can do is dy with respect to x, 2x plus 7. So how can I use chain rule? Well, they want to know dy dt. Dy dt by the chain, see I'm making a little chain, is dy dx, which I can do, times dx dt. Because if I were going to cancel, which I'm not, see how those would cancel and the two sides would be the same? So how does that work? Dy dt is, or I should say at 1, Actually, that's not the notation. The correct notation is this, at x is equal to 1, is dy dx at 1 times dx dt at 1. So dy dx at 1, dy dx at 1 is 9. Dx dt at 1, they just gave it to you. When x is equal to 1 and dx dt is 1/3, 1/3 is 3. All right. I'm going to write the answer to this one in case you would like to try it on your own. Write an equation for the tangent to the curve. As soon as I see you write an equation for a line, so this really, they're a little lazy, get used to this. Write the equation for the line that is tangent to the curve. As soon as I see that, I write my answer over here. I've got some kind of a slope times x minus something plus something. At the origin. This is fantastic. I can already fill stuff in. Really, all I want to know is the slope. So y is equal to sine of wx. Y prime is equal to sine of wx times the derivative of the inside, w. And then at the origin, y prime, cosine, cosine of wx times w, the derivative, so now look at this, I'm going to change my notation. This is where f prime is better than y prime. F prime at 0, because I'm doing the origin, is cosine of w times 0 times w. Well, cosine of 0 is 1, so the derivative at 0 is equal to w. That's what goes there. And my final answer, if I take out all the zeros, is just y is equal to wx. If you're thinking, why was this one in this section? For two reasons. Number one, it was another example of derivative of the inside, which you've been doing for a while. And two, you're going to see one of these as often as I can put them in there. Writing the equation of the tangent line is one of the biggest things that we do. What does this look like? Here's sine. And how does it change if there's a w? It just gets steeper or taller. So at the origin, this is the tangent line. It's right there. I didn't draw that very well, but it's just barely touching it. There we go. But if I made it steeper, if w is, say, 4, and this trig function is really steep, then what is that going to do to the line, the tangent line? It's also going to be really steep. That's why y is equal to wx. So hopefully the answer makes sense. The more you're willing to draw a graph and let the answer make sense, the more successful you'll be. You almost made it, last one. So this is just like number 4 that we did a few minutes ago. So if you would like to try it on your own, you can. But I can't tell you the answer. Oh, show that the meteorite's acceleration is inversely proportional. Because I don't have the answer, but it's a show. That's why I didn't write it down. So the acceleration is inversely proportional. That means on the bottom versus directly proportional, which would be on the top, to s squared. But there's going to be some kind of constant up there. That's what you're trying to show. So remember, SVA. As soon as you see velocity, just write SVA off to the side. But velocity is the derivative of s with respect to t. And acceleration is the derivative of velocity with respect to t. So my original problem says the velocity of a heavy meteorite entering the Earth's atmosphere is inversely proportional to the square root of s. Inversely proportional means that as one goes up, the other goes down. When it is s kilometers from the Earth's center. I want to know the derivative of velocity with respect to time because I want to know the acceleration. That would give me the acceleration. But can I do dv dt? No, I can only do dv ds, which is negative 1/2. So velocity is equal to negative 1/2 k s to the negative 3/2. But this notation is bad. That's still velocity. I shouldn't erase that one. The derivative is with respect. You don't need to write this all the time, just when you have different variables going on. This is the derivative of velocity with respect to that s. Well, that's a problem because I need to know dv dt. So where's my chain rule? dv ds times ds dt. So dv dt is dv ds, negative 1/2, k is on top, s to the 3/2 is on bottom, times ds dt. And this is that tricky thing again. ds dt is velocity. So velocity is k over square root of s. What does this become? Negative k squared over 2. And if you have s to the 3/2 times s to the 1/2, you add their exponents and you get 4/2, which is 2. Did we show that the meteorite's acceleration is inversely proportional to s squared? Yes. So there's some kind of constant here. Everything else is just a constant. The only variable is s squared. So we showed that it was inversely proportional to s squared. Really tricky lesson. Thanks for hanging in there. I really don't want you to sweat it out too much. You'll find that the chain rule homework has a lot to do with the parts that were much more straightforward. So have a great rest of the day.